Now comes the most interesting part is the Gaussian mixture model. So as I mentioned in start of the lecture, that this is the foundation of generative AI as well. And why foundation? Because here you are not only clustering, you are trying to get a model out of the data. And if you get a model out of the data, if you can extract a model, it becomes a generative, because now you can generate more data because now you have known the model. So that's why it is intricate, and it is important that you are trying to extract a model. So it's not clustering, simple clustering, you are trying to extract a model. And here the model is Gaussian mixture model. Like many Gaussian distributions, you are assuming that the data is distributed as Gaussian mixture. Mixture as you make a mixture, so it is just mixture of Gaussians. Okay. So we need to now really get into the Gaussian to really understand what Gaussian is. Okay. So Gaussian, as I started again my lecture by telling you and dedicating this lecture to Gaussian and how he came up with this expression for finding the probability of error distribution while he was basically measuring the orbit of a falsely discovered planet, which later they found out that it was not a planet. It was just a they call it something else, was not a real planet. So, but he could actually able to figure out that where are you going to see it again based on all the measurements they already had. And this error, he said this error is distributed as Gaussian. So this error where you could find again the so-called planet was Gaussianly distributed. So most probably it is going to be here, but it could be anywhere here and here, depending upon the spread of the error and the type of the measurements that they were taking at that time. And it was amazingly 1801, and Gauss wrote a book which is about 425 pages. And I saw actually that book. It is translated in English. It has like full of maths, like sine and cosine and hyperbolic and derivatives and integrals, and just deriving an expression which resulted into this. That was just amazing work of maths. And that is what, and I think Gauss was only 24 years old at that time. Once he took this challenge and started just driving that way, should again we find that this piece or this planet. So this is the Gaussian distribution, and so it has x is our random variable. Okay, as we know, a random variable is something which can just assign a value, an outcome of an experiment. If x is the marks you obtain in this course, all final marks, so this x goes from 0 to 100. If it is height of a person, it is height of a person. If it is weight of a person, it is weight of a person. So x is a random variable. So it's a variable, so you can plot it. It may be continuous or discrete. So because this is a variable, and like we write an equation y is equal to mx plus c. So where x is a variable and you can find value of y, which is a function of, you can also write y as a function of x, because it is a function of x. And putting different values of y, where m is a constant, c is a constant, you will draw a line. So you will find a line depending upon value of m and c, where c is the y-intercept, m is the slope. Similarly, here there are two variables. One is mu, like m and c, and the other one is sigma. So these are the two only parameters which will change the shape of this curve, and this curve is a Gaussian or a bell looking curve. So the problem is finding out mu and sigma from the data, and the bigger problem is finding out if there are more, the data has more of these, okay, more of these, and I'll be giving you many examples today. Then how do you find out how many of these are there, and how to find out that actually a Gaussian is the right representation, and how those Gaussians are distributed in the data, and finding a model. Okay, so Gaussian mixture model is generative model. that assumes that data is distributed as Gaussian mixture of Gaussian, maybe 10, maybe 100, maybe 1000, maybe millions of Gaussian. It depends upon how big a data set you have. But basic assumption is that it's just a mixture of Gaussian, and you have some way of finding out all those Gaussian. Okay, that is your model. And if you could do that, then you can generate more data. So in practice, the data distribution might be multi-model. They may not be just one, even if it is a one-dimensional data. You may have multiple Gaussians in one-dimensional data as well. And one example is if it is price of a book and the same book comes in a hardcover and a soft cover, okay, and the price of the same book is different. So people are buying a hardcover copy or a soft cover copy. And once you plot it, all the books which are being sold, you may find two Gaussian. These are the books which are low in price, maybe Asian edition, then you have another Gaussian in it. So these are the books, and if you go in Pakistan, these are the books which you find from Urdu Bazaar. Okay, then these are the books with the Asian edition, and these are the books which actually are the original copies, which are very, very expensive. So you find like three Gaussians in the data. So going to be Gaussian because the price of a book would just change like a Gaussian. Even if you are going for a locally printed book, a pirated book, you will find its price changing from 50 to 600, 700 rupees, and then there will be some average depending upon that how many books are there. Usually once you plot the data, and usually you plot it as a histogram, and you will be able to just see that how many Gaussians you see. And that will also tell you that what different type of data you have in that, whatever data you are studying. And can you actually put the model and put a Gaussian, multi-Gaussians, a mixture of Gaussians in it, and and because it's a probability density, so once area under all of this should be 1. Okay, so you got to find out the distribution, how much contribution of first Gaussian is there in this data, and how many contribution of the second Gaussian is there in the data, because overall it's a probability density function. It must, area under the curve must be equal to 1. So you got to find out the right split. So that's the challenge. So we know that a Gaussian distribution is written as also normal distribution. There is a random variable, but basically two parameters. One is the average, the other one is the standard deviation. If it is multi-dimensional data, okay, if it's a multi-dimensional, the height and weight, for example, and if there are more features, if it is a patient and there are more features, then it is the covariance matrix, and we shall be looking into the covariance matrix more closely. And here is that how many Gaussians are there in the model. So the data will tell you that how many Gaussians are there in the model, and this is the contribution of a specific Gaussian in making that mixture. So this summation is telling you it's a mixture. A summation is a mixture, mixture, once you mix it, they retain their own characteristic as well. Okay, but it becomes just a mixture. It tells you how many of the Gaussians are there, how many Gaussians are there, and a Gaussian has only two parameters to characterize it. It's a mean and a standard deviation.
This data would be of different domain?
It may be of different domain depending upon what you are trying to target, and may be of same domain. Okay, I'll show you a few examples. It may be the data that you are trying to model. See? So if it has different domains, then there will be very separate Gaussians in that data. So for example, you say if are totally uncorrelated, like the weight of a person and the weather or the temperature. So you may have like these two which are totally uncorrelated, and they may both be Gaussian. So you say, no, but this is the data which I have. So every point is, for some reason, you are keeping the temperature and the other reading. The algorithm by itself should be able to figure out that there is a character in the data that you have. This is one Gaussian, and the other parameter is creating its own Gaussian, and they both are independent. So once you plot them, you can see that this Gaussian is independent on y-axis, and the Gaussian on the x-axis is different, or both are Gaussian. Once they combine, they make a shape still. Okay.
What would be inference? What would be inference?
Inference, if like intentionally you are trying to find out the inference, there will be inference. If there is none, then the PCA and other would just throw one away. The principal component analysis finds out there is hardly any discernibility of one, helping you to, if it is labeled data. So it will tell you that this is not really adding value, it's just a noise, it's just creating noise. So you should just able to remove that, because it is, instead of helping, it is corrupting your data and it is corrupting your decision making. So, so here is again, this is the mixture, and because it's a mixture, again the overall has to be 1. So if there is a contribution of one is more, then the contribution of the other will definitely go down. So here is generative, like learning, and now you are generating data. Learning a distribution, you can generate new data samples because they are Gaussian. So you can just generate more samples, and that's how primarily all the things that we, even the ChatGPT, all the faces, the software is generating. So those are all generating modeling, where they have learned how to basically model the data they have, and now they are able to create new samples. And I will show you a few simple examples, then we can, as we progress in this course, we'll get to more intricate problems as well. So Gaussian is, we understand two parameters. Once they are changing, because area under this curve has to be 1. So if you are spreading, the Gaussian is more sigma, so its height will reduce, because area under the curve has to be 1 for one Gaussian. So it depends that how much is the spread, which relates to sigma, and that will define its height as well. And its mu will decide its location. So spread and location, and area under the curve is going to be 1 all the time. So I asked ChatGPT and to just plot 5 Gaussians for me, Gaussian distribution with different means and standard deviation on a single plot. Just wanted to see, so that you also see that this is Gaussian. So this is the code where NumPy is, we'll learn about this in our next, maybe today, that this is also a library. Somebody has done all the hard work for you so that you can just simply use it. So this is for plotting, and here is the function. Remember, you define a function Gaussian like this, and these are the parameters you pass: x and mean and standard deviation. X is your random variable, the data you got to supply it, so that it'll put it in this expression. And as you can see, it is just the formula that we have studied, simply that formula. And x is coming as a vector, so the vector you are passing the mean and the standard deviation, and this is where you are generating the data. Okay. And here is, you have 5 means and 5 standard deviation. You can go and change these as well and run this code again and again. And here is, you are putting them together and passing it to this function Gaussian and then plotting it. So once you plot it, and this is where I actually ran it on the IDE, and these are the Gaussians which the code that ChatGPT has generated. These are the Gaussians. Okay. And then we have seen, like, Gaussians is everywhere. We have seen weight and diameter of the head, the foot, the height of individuals, the intellect, so everything is bell shaped. But it became more intricate. Like here you see, apparently there are mixture of 2 Gaussians, and they are kind of tilted, mean that their covariance is also not simple, it's a full covariance, and we will learn about that. So figuring this out is the job of the modeling, that figure out that actually there are 2 of these distributions, and as we were discussing here, there are like 2 different type of people. Maybe these are healthy people, or maybe these are not healthy people, these are healthy people, and these are 2 of their parameters, maybe they are red blood cells, or something to do with 2 classes of population, in the data, and the Gaussian mixture model is showing you the both, that this is one class and this is the other class. And it is very hard for k-mean clustering or any other clustering to cluster them in this manner. No other clustering algorithm can actually cluster this data correctly, okay, because definitely it is going to make all of this in one cluster, because it would fail to understand the actual distribution of data, that these are Gaussianly distributed data. So whether it is k-mean or hierarchical clustering or DB scan, they all are going to fail in coming up with the clustering or partitioning. So usually how do we, once given data, and this is just a technique which people have been using for ages, that given data, how do you figure out that what are the different parameters like mu and sigma in this case, and deciding about the distribution, okay, the distribution. So this is somehow some experienced person, if he's just looking at it, he has to say, oh, here is the link that I've taken it from this link. It's a nice article, you can read it yourself as well. And he's saying this is the data of 10 students taking time to answer a specific question in the exam. And looking at the data, it seems like most of the average, on average, this is where the average is. The most of the students are clustered here, so they would solve it in the average time. And there are few who are taking more time, and there are some very few sharp students who have just done it in very little time. So looking at this data, it seems that it is Gaussianly distributed. With more data, you can see the Gaussian more clearly, but he said, let's assume that somebody is saying this data seems like as if it is Gaussianly distributed. Now you are left with finding out mu and sigma, two parameters, okay. And there, this is a technique which is used in probability, which is called maximum likelihood estimate. What is the maximum likelihood of, if this is we have decided that this seems like a Gaussian, then what is the best Gaussian that fits into this data, okay. It is almost same as we do regression. Once you have points and we say what is the best line that fits into this data, what is the best line that fits into the data, and then we try to come up minimizing the error, and we say, okay, this is the best line that fits into the data. But here the problem is more difficult, because here it is not a straight line. Even straight line is quite complicated once you have number of observations and you have to fit a line. So you, for example, looking at this data, what do you think, which seems like the best Gaussian to fit into the data? Here, this, or this? Pink, this? Blue. I think blue, because this point, they will also come, and here is, so apparently blue, but by even drawing it really means nothing, because you got to have some mathematical way of figuring out mu and sigma. So this is usually how the maximum likelihood estimate is written, that you have a point, 10 of these points. Using 10 of these points, you got to find out mu and sigma. And obviously, you have to put these in X here, sigma, mu and sigma are unknown. Even if you put 10 of these points, you will have 10 equations with 10 unknown, okay. If you put 10 points, you will have 10 equations with 2 unknowns, sorry. But those 2 unknowns are over exponential, and they are square of this, and it will be very hard to find out by just having those. And because they don't fit onto a curve, they get closer to the curve. They don't exactly fit on the curve. They are not the points on the curve. They are just, you are just fitting a curve on those points. So that's why they use maximum likelihood estimate. How you do maximum likelihood estimate? Let's say if there are 3 points, and these points are, let's say 9, a student spend 9 seconds, another student spend 9.5 seconds, another student spend 11 seconds. So instead of 10, you have only 3 students, your data of 3 students, and a student spend 9 second, another 9.5 second, another 11 second. So you just put 9 second here, you put 9.5 seconds here, you put 11 seconds here. Okay, and you say this is called the joint probability density, and where we assume that they are independent of each other, like somebody is not cheating the other, so one does not depend upon the other, that once he will complete, then I will complete, then he will complete. Okay, so they are independently based on just that they are trying to solve that question. So you multiply them together. Okay, so and then you try to maximize this. If they really fit in, the mu and sigma should maximize this value. Okay, they should really fit in. So maximize this value, and you say for that you got to take, as we know, the derivative of this expression with respect to sigma, and then derivative of this expression with respect to mu, and then you put the derivative equal to 0. That's how we do the optimization, that if there are two unknowns, you take derivative with respect to one unknown, then derivative with respect to another unknown, and put the answer equal to 0, two equations, solve the two equations. So here, but again it becomes very complex. So what people do is that they take log. Once things are multiplying, you take log, they converts into addition. And log is good because if something is increasing, its log will also be increasing. If something is increasing and decreasing, its log will be also do the same. So the maximum point will not change because you are only trying to find out the maximum. So by taking log will ease you out and will still maintain the optimal point. Okay, so that's the trick which is used, which is called log likelihood estimate, and you take a log, and once you take the log, all multiplication changes into addition, and exponential log cancels out. So you get all this. So all the powers get out of the exponential, they get down from the exponential goes away. Now it becomes a very easy expression to actually work with. And so you just take the natural log, and then you take the derivative with respect to mu and the derivative with respect to, and you find out, and this is interesting, you find out which you already know, that average is, the mu is adding all point dividing by 3. So we already know this. But now this also strengthens your belief on this, that actually really the mu is the average and the other one is the standard deviation. So you can generalize this maximum likelihood estimate, that if you have n points, okay, and so this is obviously this is important because we are trying to fit a model in the data. And if you have m points and you are told that these points are part of a Gaussian distribution. So 2 parameters, log likelihood says it is very easy to find the 2 parameters. One is the mu, add all the points, divide by the total number of points, and the standard deviation, subtract it from the mu and square it, and then just add them and divide by the total number of points. So we already know this, but there is a strong mathematical reasoning behind this formula, which is the maximum likelihood estimation. So which says that if you have all these points, putting in this expression which has the probability density function and multiplying them together, taking the log, finding the maximum, will result into, this is the expression, will result into the same. You put curly mu equal to 0 and curly sigma square equal to 0. So we already know these expressions. Okay, so I don't want to get into the mathematics of this, but you must know that this is coming from a very strong mathematical reasoning, that if you have n data points and you want to fit a Gaussian, okay, all you have to do is just add all the points, divide by total number of points, will give you the average or the mean, and subtract every point from this mu that you have calculated, square it, and keep doing it with all the points. Add all these squares together and take the average, will give you sigma square. It's that simple. Okay, so from the data, finding out the distribution is not difficult. Okay, because if you know mu, if you know sigma square, you know you can just plot it. This is at mu and spread is sigma. So you can just plot the distribution, and that's a good part. Okay, so for example, this is where you find out, like if you are a student and you are taking 2 courses, okay, or all the students in a course they have a marks in one course, maybe a linear algebra, statistics or whatever. And you see that how they perform. A student getting good marks in one subject and good marks in another subject. But you may still find a student who gets very, very poor marks in one subject, poor marks in one high. But usually those who are good, they are good. So it is tilted towards this. So if somebody is good in one subject, he is also good in another subject, but it is Gaussianly distributed, but it depends upon each other. It's not independent. Like it is not that this is an independent Gaussian, and this is where your answer to your question is. Like they may be independent and they may not be independent. If they are not independent, okay, one depends upon the other, because if you are good in one subject, most probably you are going to perform good in the other subject as well. So it will be tilted in this direction. Okay? So it means that you're good, and if it is otherwise, it will be tilted in other direction. If negatively correlated, if you are fat, you may have this disease, for example. So increasing other will basically is bad, so to say. So this is where. So and once we say that once you are sampling, so you have a humongous amount of data. We say IID. So this is a terminology which is used a lot, like independent and identically distributed. So if you have a data where you have data of different people, okay, and you only want to select some samples, you have to randomly select. You got to ensure that you're not only selecting, for example, if it is a Lahore board and I want to do some student statistics and I only collect samples of very intelligent students or very poor students, that will not really give me the true statistics. So I got to, even if I'm sampling, I got to make sure that sample is independent and identically distributed. From each group I collect some samples, okay, and only then I'll able to make a good model. Otherwise the model will not be good. Now comes what if it is Gaussian is two-dimensional, okay. We have just seen it. Exponential remains exponential. Because it is two-dimensional, x will become two-dimensional data. For example, if you have height on this side and height and weight on this side. Okay, so for every sample, you have two parameters, height and weight. And for 100 individuals, you plot them here. Okay. So every sample is a two-dimensional data. So there will be height, let's say 5 foot 7 inches, and weight, let's say 82 kg, for example. Okay, so 2. So means x is a vector, mu will also be a vector. Once you find out its average, mu will be a vector, and this sigma will now be a matrix, and that is also important to understand. It is going to be a matrix where this will be your sigma square x is your spread in x direction. This will be your spread in y direction. If you just see only the y points, it means you only see the weights, and they will also be Gaussianly distributed. If you see only height, height will also be Gaussianly distributed. So you find independently, you find how the height is distributed, how the weight is distributed, but then they will be related to each other. Okay, if they are, then there will be something here and here. If they are not, there will be a 0 here and 0 here, and that's something which we need to understand. If they are not related to each other, they are independent parameters, then you will always see a 0 here and a 0 here. Otherwise, you see something here and something here. Once you see something here and something here, it is called full Gaussian distribution. And it becomes, as the dimensionality increases, it becomes a very, very difficult problem to solve, to finding out all the parameters. And because all these are unknown. Okay, sigma is unknown, mu is unknown. And it's a mixture of Gaussian. You don't know even that which point belongs to which Gaussian. Okay. So it becomes a mathematically intractable problem, very, very complex problem. That's why this generative AI modeling takes sometimes days and days of computation to converge into something where it has to find out all these parameters to model the data correctly. Okay. So if it is even n dimension, So it is not height, weight, your salary, okay, the calories you consume every day, the walk, and so you're just putting more and more and more parameters. For some reason that the data has, every sample has now more parameters. Once every sample, usually this is the case, once you're doing machine learning, AI, you just throw in all the parameters which you believe will help you to make a decision, okay. There may be many of them may be irrelevant, but so if all of these may independently be Gaussianly distributed, that is fine. If they're independently Gaussianly distributed, then I have no worries. But if they start relating to each other, one relates to 2, one relates to 3, one relates to 4 also, 5 also, 6 also, 7, then my life will be very difficult, okay, because then I need to find out all these correlations as well, cross correlation. This is 1 with oneself is fine, but 1 with 2, 1 with 3, 1 with 4, 1 with m will becomes very, very difficult problem to solve, okay. So is the mu is going to be a vector now, and this expression x is a vector with n parameters, and x is a vector with n parameters, x is a vector with n parameters, and you are trying to now find out a Gaussian distribution into this data, okay. So here is if it is, this is a general Gaussian, okay. If you are thinking yes, there is something here as well and here as well, and if it is 2-dimensional, you are going to see a tilt, okay. You are going to, this is how the x and y, if they are correlated and positively correlated, and like this if they are negatively correlated. If they are not correlated, you will find either this like this or like this, okay, like this or like this, depending upon which one is greater, whether sigma x is greater, so you will see it like this. If sigma x is more spread than sigma y, so you are either going to see it like this or like this, okay. So here is if you have only 2 sigmas and sigma x is smaller and sigma y is greater than sigma x, you are going to see this distribution like this, right. So if you look in the 2 dimensions, so it will be a hill, but that hill will be very sharp, more in that direction and very less in this direction. If you look from here, it will be a hill like this, and if you look from here direction, it will be like this, okay. Like if you are looking at this hill from this side, it is very long, but if you see it from the GT road, it's very thin, okay. So it's like kind of Gaussianly distributed, and it behaves like this. So this is if all these sigmas are normalized. So usually we normalize all the features. Every feature goes from 0 to 1, so that it must not create any bias. Otherwise, weight is in hundreds and height is in only 5, 6, 7. So it may just bias once you're taking distances and stuff. So usually we normalize this. And if you can assume that after normalization, after making everything going from 0 to 1, your sigmas are coming out to be the same spread in weight, same spread. So your life becomes very easy, right? Because there is only one unknown, which is sigma. And you are assuming that it is for every data point, because it is normalized, it has the same spread. So the problem, though it is still multi-dimensional problem, but the parameter you have to find is only one now. So you can basically take any distribution, just wait and you find out sigma. So my assumption is that this is normalized data, and sigma for every dimension has the same spread, right? So becomes very, very easy problem to solve, and because now you have only one parameter. Mu is definitely mu and sigma. So you say I can now easily find this out. So here this is called this is called diagonal, this is called spherical, and this is called full. Full mean it is tilted in any direction, okay, tilted. Spherical means one only sigma square, only one parameter sigma, and in both direction it is sigma, so it will create a circle. If you look, and these are all the data points, and you see they are more crowded here and less crowded in the spread, okay. And this is where you have the distribution is like this, more spread in y direction, so x direction, so sigma x here sigma y, but it is like this, right? So I asked ChatGPT, this is the code which I generated last night, generate Python code to plot 2D Gaussian distribution for some mean covariance matrix, generate distribution with all the three types of covariance, full, spherical and diagonal. Okay. So this is what I asked ChatGPT to generate so that I can just see and experiment with this. So this is the code which ChatGPT generated, and if you look at this, so almost the same. Here is the generate Gaussian function. It is, you are giving it mean. Now covariance matrix. You got to provide it a covariance matrix, now a 2 by 2 covariance matrix, and you got to tell it what type of distribution you want from it. So full, this or this. So so there is a full, there is a spherical, there is a diagonal distribution. Okay, and then here is the data. It is for the full. It is a matrix which says 1, 0.5, and it is always a symmetric matrix 0.5 and 2. So we see that it is a matrix where you have this different from this and this are to be the same, because this is sigma x y cross correlation. This will be a symmetric matrix. So this will give you a full like this, and then here is so this is where you have a spherical 2 and 0, 0 and 2. Why? Because this is same, this is same, this is 0, this is 0. So only one sigma. So you are assuming spread same on both sides. And this is where you have a diagonal 1, 0, 0, 2. These two are different, because now these two are different. You are going to see a different elongated on one direction, less in the other direction. So here is the code that I ran, and I got these distributions. So this is the full covariance, which is this. This is spherical, and this is more like this. Okay, so you get three different type of distributions. I ask it to give me a 3D plot. Okay, then I put this prompt. Can we also plot these distributions in 3D? It said yes, this is the 3D distribution. Then I ask it, can we do a counter plot? Because in many places you see a counter plot. Like counter is where you have elevations mentioned on every counter, on every line. And definitely there are, the spherical is going to be circular, and here are the values of each. Okay, and here is the full, and here is the diagonal. So you can plot these distribution in three different ways, asking ChatGPT to do it, and I'll very easily do it. Okay, so this is good that I'll be giving you this as an assignment as well, so that you just, and maybe from the data you may be able to just get this. Ask it to fit this as a spherical. So I'll put a spherical. It'll assume sigmas equal to 0, and it'll just put a. So you can always have those approximation. So now comes the difficult part. Okay, this is the difficult part, that if you don't know which data point belongs to which distribution, so it becomes a difficult problem to solve. Okay, we'll see how. And here is this expectation minimization method, which will try to help us out. So you have this is the data that we have been seeing for every clustering problem, and if I want to fit in a generic Gaussian, so I can see, like, it seems like this is a Gaussian, it seems like here maybe a symmetric, a circular, a spherical, seems like maybe a spherical here, a spherical here, something like this. It's like kind of, if I'm just, I should be something like this. So this is, and if I have mixture of 1, 2, 3, 4, 5, so maybe a Gaussian which is diagonal like this, a full like this, maybe a circle like this, a diagonal like this, a diagonal like this, maybe, you know. So it depends that how many Gaussians I try to fit into the data, and how to evaluate is the knee, that you find out the cluster heads, and then you find out the distances, and then you can find out that how many Gaussians are basically best to describe this data. This is a problem which I am just to explain. Let's say I want to model the color of skins of Americans and taking two type of Americans. One is African Americans, the other one is white American. Okay, and I, instead of going into the color space, making my problem difficult, I convert a colored to a grayscale image because I want to deal with one-dimensional Gaussian instead of a two-dimensional Gaussian or three-dimensional Gaussian. If you do color, then you got to have three channels, RGB. Then you got to have every data will have three. So this will become a covariance matrix which will be 3 by 3. So it will be red, green, blue, and problem becomes a bit more intricate. So this is a problem, and this is the colored image, and it's just an example. I have not actually done this. Okay, just to explain, and so that we can connect it with this particular example. Okay, so here is the grayscale, and so what I do is I take his face or part of his skin here, patches of his skin, and all these samples together and divided by total number of samples. So average skin color in gray. Similarly, I take his skin 3 or 4 patches from his skin and add all these, so that now every image will be just one value which represents color of his skin. Same I do here, here. Okay, so for every face I represent every face as a data point as in my data set. Okay, so every face is just one value, in which I have done some image processing, face detection, taking 4 patches, adding them together, and so I have, if I know, okay, one is I know that this is coming from African American, this is coming from a white American. So this is, here is 0, which is pitch black, here is 255, which is totally white. So all these are gray colors. So I am placing a face. So a point is a face. So I know this is African, this is African, this is African American, African American. But here is an African American which gets into the other distribution, where there is a quite possibility that he is not that dark. Okay, so he is a bit fair color, and similarly there is a possibility that one white American gets into a little on this side, and he is not that white. Okay, so but this is white American, white American, white American, white. I know the distribution. Because I know the distribution, it is very easy for me to fit a Gaussian, because I know, all I need to know is mu of, let's say this is mu of A, the yellows are A, distribution A, and sigma of A. How I compute mu? Add all these pixel values and divide by total number, which is 1, 2, 3, 4, 5. And and this is the B distribution, which is the white Americans. I have mu of B and sigma of B. I know how to compute mu, I know how to compute sigma. So I compute it and fit into Gaussian. The problem is very simple. Okay, so here is, I have this one face is a point, and this one face is a point. Let's say she is on one extreme of my axis, and he is on one extreme of my axis. Okay, and so let's say her skin color is 10 and her is 180, for example. Okay, and this is my random variable, which runs from 0 to 255. So every face is a point on this axis, and I want to model it, so that once I model it, then I can create more skin colors, so to say. If I correctly model it, I can create African American, I can create white, and if I put Asian, so there may be 3 distributions. Okay, so I can very easily just find this out, and I can just combine them together to have a mixture. So this now becomes a mixture of Gaussian. So this is a Gaussian mixture model, and there is no challenge in this. No challenge. There is no challenge. It's just matter of like few millisecond, nanosecond for the algorithm to give me the mixture of the two. And so this is the formula I use. So estimation is trivial if we know the sources. All I need to know is mu and sigma, put them in this plot. And how I know mu of this distribution? This is, if this is 1, this is 2, this is point number 3, point number 4, point number 5, point number 6, point number 7, point number 8, point number 9, point number 10. So for the blue case, I need to add 5, 7, 8, 9 and 10. 5, 7, 8, 9 and 10, and they are total 5. So I get the average, and then I have every point subtract by this mean which I have calculated. Every point subtract with this mean, divide by 5, get a standard deviation, put it in this formula and plot it, and that's it. So once you plot it, you get this, and similarly you get the other distribution by having other points, which is point number 1 and 2 and 6, divided by 5, and similarly finding the distribution. Now is the challenge, and remember that if you don't know that which point belongs to what. So now we need to go and learn what we did in k-means algorithm. If you remember, in k-means we said let's have a two centroid, one is here and the other one is here, and assign a point to the closest cluster. So we assign it this point here. The 8 was one cluster, sorry, and this was the other cluster, and the point was perhaps somewhere here or somewhere here. And then we started saying that this is, add all of them together, find a new centroid, and once you have a new centroid, now do the assignment again, and here is the new centroid, do the assignment again, and you will find out the point which was in this distribution went into the other distribution. And then we said, okay, do it again, do it again, do it again and again, and we saw a natural kind of distribution, extracting the natural distribution, that there was a cluster of 2 points here, and this is where we started with the cluster of 3 points here. Okay, so it was very easy problem because all we have to do is just compute the distances, and it was not difficult. So compute the distances, and finally we get the allocation. Here it becomes a more challenging problem. Let's say all these faces, okay, because I don't even know, they are not labeled, okay, they are faces, they are like 10,000 pictures and they are not labeled, and I don't know. I do the same thing, find out the face and extract the face color, add them together, do the average and plot it on this line, okay. And now I want to see that how many actual Gaussians are there and how do I fit in a Gaussian in this, okay. So this is where we need to go take help from the Bayes theorem. And remember the Bayes theorem, you say first you should have some initial belief and then keep refining the initial belief, okay. So you have some initial belief and then you just keep refining the initial belief based on the iteration or the data or the more understanding you start getting. So you take help of the Bayes theorem, and this is the EM method if we don't know the source, and this is kind of the modeling, extracting a model from the data. That's how we extract a model from the data, okay. So set some initial belief and then keep refining it. Okay, for example, I say there are 2 Gaussian distribution and I just randomly place it anywhere. And I say there are, half of them are African American, half of them are white American. So this is my first part of the initial belief, is the distribution of the mixture. So how much is the probability that something belongs to distribution A? I am saying it is half. Half of them are black and half of them are, this is my initial belief, okay. And I say this is my initial, first belief is half of them are half of them are white, half of them are black. So I have prior probability, my initial belief that this is the distribution, okay. My second belief is there color, the average of, let's say, A is 5 and average of B is, let's say, 10. Just any random number. Okay, you may have intelligent guess, you may have a dumb guess. You say, this is my second assumption. My third assumption is, let's say the spread is sigma square is 5, sigma square is 7. Sigma square of A is 5, sigma square of B is 7. Initial belief that this is how the African American are spread less, white Americans are spread more, maybe just an initial belief. So with this initial belief, I get into the iterations. So belief on the two probabilities, which is the value of the mixture, that how many belongs to this, how many belongs to this, and then their Gaussian distribution, because these two parameters define the distribution. These two parameters defines the distribution. So I start with this thing, and because I know the Bayes theorem says that if I have my initial belief, okay, and based on this belief that half of them are this, half of them are this, I can find out the probability of the other given that I have created this distribution A. Then I can find out that what is the probability of A given B, and usually this is computed by this total probability theorem, which we have seen it. But let me, here is the way we have learned it, that there is an initial hypothesis which is called prior probability of hypothesis. In this case, we are saying half and half. Okay. And based on this hypothesis, I am going to update my hypothesis. Based on the evidence, I update my hypothesis. This is where we saw the 9/11 case. We said there was hypothesis was that no aircraft can actually come and hit the Twin Tower. But once the first hit, then everything changed. That now there is a probability. Or second one hit, then you say no, there is a 99% probability they are the terrorists. So you strengthen based on the evidence, you strengthen the hypothesis. This is what we have learned earlier. Okay. So let's just 5 more minutes and then we'll take a break. So here is, now I have written it in terms of my data. My data is, wait, okay, so now let's consider this person. Okay, this is a person, and let's he is x1. Okay, and I have this distribution and this distribution. I have two distributions to start with. Okay, maybe I have totally wrongly placed them, because without any a prior knowledge, I have just randomly placed two distributions. Okay, so, and I know I have assigned half to this, and I have also assigned average to this distribution and average to this distribution. This distribution is for white American, and this distribution is for black American. Okay, and now I want to see this point. Okay, should I assign it to white or I assign it to black, as we do in clustering? Okay, I want to assign it to one of the distributions. So I can assign it to white or I can assign it to black, and maybe I have to assign it to the both, because of the way these distributions are. Maybe a very little part of this will get to black, and a majority part of this data will be to white. So what will happen here is that in this, there will be a soft assignment. Means a point may not be totally assigned to a distribution. Okay, for example, if there is a point here, it will be split. At this point you don't know. Half it seems like black, half it seems like white, because the way these two distributions are placed. Once this distribution will start moving, so it will get closer to either black or white. Okay, definitely they are going to move if they are really Gaussian in nature. If the data is Gaussian in nature, automatically they will move to their respective position. But to start with, you don't know. Okay, so they may be totally wrong assignment, as was the case in the k-means as well. We saw in k-means that a point was assigned to one distribution and then slowly half of them move to the other distribution. The same will happen here. But how do we figure out? Okay, this is the way you figure out. You say, okay, this is the probability that a point is going to be a white. So this person is white, there is half probability. This is what I have seen, half probability. So probability of any point to be a white American is half. So put probability of B as half. Okay. So what is the probability that this point, this particular point, which has, let's say, gray scale value of 10, what if this variable of 10 is part of this B distribution? What is the probability? I know the formula, Gaussian formula. For this curve, I go and put value of 10 as x, and mu I already have mu, and sigma I already have sigma. I have mu, I have sigma, I have x, and I also I'm putting a condition that it is a white. So what is the probability that given I'm saying he is white? So this is actually white. So I just put this point in this formula of this distribution, which will give me this one. Probability of xi, probability of this person, kya hai if he is a white American, given the distribution is white. And for the other case, for the same point, we will do it for black as well. So you got to do, as we were computing distances from all the centers, what is the chance of this to be assigned to this centroid? What is the chance to be assigned to this centroid? But there the formula was very simple. It was a distance formula. Here the formula is a bit complex. Right? So you do this. So this is fine. This is fine. This is fine. Probability of xi given B is fine. Probability of B is fine, which is half. This is also fine. What is the probability? This is actually part of the distribution A, which we have to put this in this formula for the distribution A formula. So this is also, and probability of A is half. So I know everything. So I put all these values here. I calculate the probability of this point xi given this point. What is its chances that it is part of that he is white? What is the probability given this point? So I am inverting. Here I know that he is white. What is the probability? I am saying here there is a person, given this person, what is the probability he is white, or what is the probability he is black? Okay. So this is what I am computing using Bayes theorem. So it's that simple. So I compute this. This gives me a value of Bi. So this is the probability of this person 1 to be a white American. Okay. Similarly, there will be A1, the probability of this person to be black American. So you can calculate both. Okay. So this is how it is done. So this is the Bayes theorem, the initial belief, and we put this point in this formula with sigma b and mu b to find out this probability that given that this is the distribution, so probability of this can be found simply by putting in this formula, and the same point given he is black from this formula. Okay, given the distribution, you find out the probabilities by only putting this to the formula. Okay, and you know this is half, you know this is half, you know sigma A, you know sigma B, you know mu A. These are all your initial assumptions. So initial assumption will have all these parameters, and that's how you get into the algorithm, okay, for the first iteration of the algorithm. So you calculate bi, you calculate ai. Okay, so you calculate b0, b1, b2, b3, b4, b5, b6, b7 till b10, b1 to b10. Similarly, you calculate from a1 to a10 for every point, every point, every point, every point. So you take this point, you take this point, you take this point, and now start coloring it, that how much this point is from the blue distribution and how much this point from the yellow distribution, so that visually you can see that this is a point which is more probable given this distribution to be a white American. So this is the probability that he is a white American, and this is the probability that he is a black American, because to start with we have placed our distribution here. So this is the assignment, cluster assignment. And as you can see, this is a soft assignment, not a hard assignment. So there is a little probability that this guy may be a black American, okay, at this stage of the algorithm. So you say, okay, no problem. This is my soft assignment. So I have, if I know bi, so I can easily calculate ai. I don't have to go through the formulas and all of this, because total probability is going to be 1. So if it is 0.8, then for this point to be a black American is 0.2. Okay, simple, that you need not to get into the whole these formulas. So here is that your distribute blue, more almost blue, and this is your first assignment. Okay, looking at this, you start coloring the circles, that because this is my distribution, it seems like. So I am done with the first iteration of the algorithm, where all these points are being assigned to a specific cluster. Now I can find out the cluster head, the centroid, which is the mu of black and the mu of white. Okay, and this mu of black was first, this is the first person, his color of skin, and I know that there is a probability a1 that this person is a black person. Similarly, here is a grayscale of the second person, and this is the probability that this person is a black person. So I assign all 10 and divide this by 10 to find out the average. In k-means cluster, either you assign it to a cluster or you don't assign it to a cluster. So ai can either be 1 or a 0. Okay, that was k-means clustering. For example, x1 is assigned to a cluster, a1 will be 1. x2 is also assigned to this cluster, a2 will be 1. No point is assigned to the cluster, they all will be 0. So that's what you do in k-means clustering. Okay, and here, so either here will be a1 plus a2 plus and a10. Okay, that's how you take the average, because in that case this is 1, so you divide it by 2. And similarly you find out the new mu as well, the mu b as well. It is b1 x1 plus b2 x2, and similarly divided by b1 plus b2 plus b10. So here are, so this we know the formula, 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 sorry, this is a distribution, and this is how you calculate the mu. Okay, as I mentioned earlier, that if it is k-means clustering, b could be 1 or a 0. Let's say this point and this point, only 2 were part of b, so x2 plus xn divided by 2, and that's what you will get. But here, because partial assignments, so you are going to see some mu b, and once you know the b1, so you calculate the sigma square b as well. But now instead of just subtracting it from mu b, and sorry, here is a square, and squaring it, you got to have a b1 and B1, because part of it is contributing, part of it is contributing, and same as the division. So you get this. And similarly, so this is what you get. So there is a square here, there is a square here, and this is what you get for mu A. There is a square here, there is a square here. Now you have nu mu and nu sigmas, and there is one thing which you need to have. What is now the probability of somebody to be a black and somebody to be a white American? And this is very simple, because if you add all the A's, okay, it will give you the probability someone is the probability of black, and all the B's will give you probability someone is white. So and take divided by n. So this is that the probability that this is the mixture, that how much the height of this Gaussian is going to be. We started with half and half, okay, and now once you add it, it will give you height of the probability of this based on, because at this stage it seems everyone is black, everyone is white. So this is going to get to the high value, and very few are black, so it will go to the low value, okay. So you calculate this, and because total probability is going to be 1, so you can do 1 minus probability of B. So this is pi 1 plus pi 2. So this is your mu B. These are the square, which I have written it with myself, so I missed the square. So now you get to the new iteration. Based on, as I said, it seems everybody was painted white American. So you find out this distribution, which was initially here, and all these points were assigned to blue. So its mean has moved here, which is very, very obvious. And because only partially this point and this point was assigned to black, so you see hardly anything, any change in this one. You hardly see any change in this one. Okay, it just is there. Okay, so it remains here, and this is cumulative density CDF. So because total probability of these distribution and this should be 1. Okay, so it was half and half. If you integrate this, because integration of this is 1 and this is 1, so half into 1 is give you 1. Okay, so this will be now the split is going to be here, and this value is the mixture value of the 2, and this value is the mixture value of the 1. Okay, so but once you add these together, this must be 1, and the area under the curve should be 1. Area under the curve should be 1, and this is why it is showing that this is the distribution. So now here is you run it again. Okay, now because now you know the probability, posterior probability you updated. Now you know the probability of nu A. So this is what we are studying, that a Gaussian mixture model, and as I mentioned earlier, that this is also the foundation for generative AI, and this is how that you are given data and how you fit a model in the data, and that's what we started learning. And I took an example where we talked about a problem where we want to put a model in basically in partitioning the American population into African and white people. And we said we have like a sample space where we have many photographs of people who are African, and they are mixed with others who are white people. And so we take patches from their faces, and then first we convert the images into grayscale, and then we represent every person as a point on this one-dimensional space. And we have two distributions. One is a distribution of the white people, and the other one is the distribution of, let me just take a pen. So one has a distribution of white American, and the other one is a distribution of black American. And if we know a priori knowledge that which point belongs to whom, so he is black and he is white, and all the yellow dots are for the black people and the blue dots are for the white people, so we can put a Gaussian, and it's very simple problem, and that all we have to do is to find out the mu and the sigma, and for the yellow dots and for the blue dots. And so these are the formulas that we use to find out, to plot the Gaussian curve. And so knowing mu and knowing sigma, and then the x that we can change, and we can generate more samples, and that's important, that once you know the distribution, that for any point now you can generate more points, that primarily because now you know the data distribution. And so we took this example where 5 of these people are white people, so we add them, find their means and the standard deviation, and similarly the 5 of them are black, and we do the same, the mean and the standard deviation. So there is going to be a square that so, and then I related it with the k-means problem, where we started by just assigning 2 cluster heads, and then in every iteration assigning points to a cluster, finding new cluster head, and then again assigning points to clusters, then again cluster head, and finally we got a final distribution, that the points which are assigned to cluster 1 and cluster 2. And we said now the challenging problem in modeling is that you are only given a data without any a priori knowledge, that you don't know that which of these dots is belong to white American and which to African American. And so you got to now, but there is this distribution is hidden in this nature, and that is the job of the modeling, to extract that distribution. Okay, so that distribution is just there in the data, and that is the premise. If there is no distribution, obviously then it is just useless to actually fit in something. So the assumption is, very strong assumption is, that the data is Gaussianly distributed. There is a mixture of Gaussian in the data, and that is something that we got to extract from the data. So I told you that we have already learned about Bayes theorem, and we are going to use this, and especially this form of the Bayes theorem where you have some prior belief, and based on the prior belief you keep updating the brief based on the evidence. So there is an iterative way that you have, you start with something, that is your initial assumptions, and then once you start getting into this iteration by iteration, you keep updating, and that's what we do, whether it is it depends that how humongous the data is. You can fit hundreds and thousands of Gaussians into that data. Okay, and if you are just modeling the data into mixture of Gaussians. And so in our case, where we started with a very simple problem so that we understand what the challenge is. So challenge is that you have a prior, so this actually is called the prior probability, that is your assumption, and based on your assumption, this is the probability that a person you picked is a white American. And you say you start with half and half, that half is the probability he is white and half is the probability he is black. So you start with this and then use this, that given that this distribution is for white American, and you have, with this assumption you also have an assumption on the mean and its standard deviation, so you can easily find out probability of xi given that B is the distribution. And this will help you to find out that given this person, what is the probability that he is white and what is the probability he is black. So that's what we are calculating for every person in the population. We are going to calculate B1, B2 and B10, and similarly we are going to calculate A1, A2 and A10. And I also mentioned that because it is all probabilistic, so for every person there will be a probability that this is the probability, because we don't have any a priori knowledge that he is white, or and this is the probability that he may be black. And this is why it is called a soft assignment. So soft assignment is where every point has to be assigned to every cluster. Okay, so that also makes the problem little bit more harder to solve. And so you basically initialize your data with two distribution like we do in k-means, and you assume some a priori probability with this, and you also assume that they have a mean and a standard deviation. So these all, once you start, you got to assume this, and this is almost the same as we do in k-means clustering, that you have just randomly place centroids and then start moving the centroids. For me, the centroid is mu A and mu B. These are my centroids. Okay, so these are my centroids, the center of my distribution, and you can assume them to be centroid, but they are not hard centroid, because hard assignment, because of the same reason that every point will be probabilistically assigned. So we saw this, that you have half probability of this, half probability of this. So this is probability of A and this is probability of B, which we shall be updating in the next iteration of the algorithm. And this is sigma A, sigma B, mu A, mu B. And now point by point, you take very first point first, and you take the first point, and here is the first point, and assuming that he is white, you find out the probability. And the same point, assuming now he is a black, which is this distribution, and you find out the probability. Or you can just do 1 minus this, will also give you the probability. So this is the probability that you calculate. So, and then using this that you have by putting the value of xi in the distribution, you have calculated this. This was a priori knowledge. So this is the same value which is used here, and this is the a priori knowledge, and this is for the B, for this point to be part of the A distribution, and this is a priori knowledge. You calculate something which is very important, and which is BI, and here is the AI. So now you have new BI, new AI, and that's something which is going to color, and this is important, that for example this is that person. So this is person 1, this is person 2 who is appearing as a point on my axis. He is just a grayscale. Maybe I said it is, let's say 10 is the grayscale value, which is running from 0 to 255, from pitch black to pure white. So everybody is somewhere on this line. So according to this assumption, this person seems more like white and less like black. And so this formula will just give us that value. And knowing this value and this value for every person in our sample space, we can find out now the probability of B and the probability of A by adding all B's together and taking the average, and adding all A's together, taking the average. Right? So that's what we wanted. I have BA, I have BB, and I have also with this I can calculate the new mu's and the new sigmas for the next iteration, because I got to know the mu's and sigmas. I got to know the new position of these curve, and so this is what we saw, that these dots will be colored, and all these, because they are towards this distribution, they all are colored blue for our initial assumption. Means all these points are assigned to this cluster, which is they all seems like white American, and this guy seems like the only, and still it has a portion of it seems like he's a white American. So this is our first iteration, and so we got to update several things. So these are the probabilities. See, these are the BI, these are the AI, and this is our distribution. This is the first thing that we got to find out. It is now the new mu B, because all these points are assigned to this distribution. Definitely mean is going to move towards these points, and this will tell, because these are the original gray values, okay, grayscale values, and this B1 and B2 is the probability of this to be part of the white distribution, and this is how you divide it. And as I mentioned, if it is k-mean, the B's I has to be only 1 or 0. Either it is assigned to a cluster or not assigned to a cluster. So, and that will just make you to understand it better, that maybe only these 2 points are assigned to a cluster. So then you will have x1 plus x2 divided by 2. And that's what we were doing in k-means clustering. But here there is now a probabilistic assignment. So you find the new mu here, and similarly you find the standard deviation here, and square and square. And so this is the mu b, this is the sigma square, and sigma square, and this is sigma a square. So now you have all the updates. You have the new mu, the new sigmas, the new mu, the new sigmas, and also a priori. You have the probability of b, and you have the probability of. This is how we started. Now we can redraw. So we have all these values. Now I can redraw. So obviously, because of all these points assigned to blue, the new blue that we have drawn as a Gaussian is spread out. Its mu has changed and more towards these points. And but this, because hardly any point was assigned to the yellow one, it remains as is. But once you do the next iteration, it is going to, because now the tail of this Gaussian is here, so a bigger part of these persons will be assigned to the black population as well. And this is the CDF, the cumulative distribution. It has to be 1 starting from 0, okay, because they are the mixture. Mixture means they should be seen as one probability distribution, and their area under the curve has to be 1, okay. So this is how the probabilities are distributed. So this will move here, and this will move here, and this will move here, and slowly but surely they are going to get to their places where the actual Gaussian is there in the data, okay. That is the premise, that if they are actually Gaussianly distributed data, so the things will move towards those. Now, so the challenge of soft clustering is that every point, okay, every sample point, point 1, point 2, point 3, point n, if there are 3 clusters, it will have 3 assignments, okay. Maybe let's say this point, it is primarily mostly assigned to cluster green, and there is hardly any, so you may say 0, 0, okay. But as you move towards, let's say this point, which is point number, let's say 19, so there is 0.8 chance probability that it is assigned to green, but then a part of it is also assigned to red, which may be 0.2 and may still be 0 to blue. And there may be a point which is assigned, which has assignment to all the 3 clusters, okay, partial assignments. So once you make the assignment table for every sample point in case of Gaussian mixture model, so you got to have a point assigned, may be assigned to every cluster in the sample space. So this is how the assignment will happen. So here is another example. For example, instead of 2, there are 3 distributions hidden in that. Okay, so just expanding the, and they may be like Asians, which are neither black nor white. Okay, so Asians are here. So these are Asians, these are white American, and these are black American. So they are black, Asians, and white. Okay, now there are 3 distributions, and so every distribution has a priori probability. So this is the probability that it is A, this is the probability that it is B, and this is the probability that it is C, a priori probability. So to start with, you can start with 1 over 3, 1 over 3, 1 over 3, assigning equal probability to all 3. That's how you start. And you can have mu1, mu2, or mu A, B, C, assign mu, assign sigmas, and almost repeat the same step. Now here you have 3 mixtures. So here you have a mixture of 3 Gaussians. Okay, so 3 Gaussians, and once you plot them, so it will be something like this as one distribution. So it is going to be like this. So you have 3. Now if we make this problem more complicated, okay, and we have already learned that color image has 3 parts: red, green, and blue. So it becomes a 3-dimensional problem. Okay, the same problem what we saw by converting an image to grayscale, we reduce the problem to a 1-dimensional problem. But I want to take the green, I want to take the colored images. So colored images, you got to have every point will be in a 3-dimensional space now, not in a 1-dimensional space. So an image will be a point in 3-dimensional space where you have some value of red, some value of green, and some value of blue. So there are going to be 3 distributions, and you may want to deal with them separately to make your problem simple, that I will deal the red separately, the green separately, the blue separately, or you got to just deal with them as a 3-dimensional problem. And remember, we discussed this, and remember we generated this code from ChatGPT as well, where we gave it a frame, a color image, and we asked it to convert it into RGB. This was the code, and I actually gave my image of visiting the Grand Mosque in Abu Dhabi and converting it into blue, green, and red image. So this is how the problem would pose itself, that you have a big database, okay, and that database is divided into 3 parts. So there are forests, there are sunset scenes, and there are sky and cloud scenes, and you have these images stored separately, these images stored separately, these images stored separately, and you say I want to see the distribution of blue color. This is a simple problem. I want to see the distribution of blue color in these images. Okay? We know that the distribution of blue color in green, because it's a forest, so there may be some skies, so there will be some part of the blue, but mostly on the lower side. The same thing, all the blue colors you are going to add, divide by, normalize it. So an image will appear as a point on this line. An image will appear as a point on this line. So you are going to add, first split this image, every image into R, G, and B. Then you are going to take the blue channel, the blue image, and going to add all the pixels. So if this is an image, and if you have U and V, so you are going to add all the pixels of this image, and then you are going to divide it by the total number of pixels and the maximum value to make it go from 0 to 1. The maximum value, which is 255 of the grayscale, so that you normalize it. So you normalize it, and you find out for blue, though it is Gaussianly distributed, this is important, and you interestingly find out, oh yeah, it is Gaussianly distributed. So there are like on average these many, but they are here, and this is also Gaussianly distributed, and this is Gaussianly distributed. So you can easily model it, because you plot them as in a few samples you may take, like ID, and then you plot them. But what if they all are mixed up together, okay, and you don't know which one is what? But once you plot, you start seeing 3 Gaussians, okay, you start seeing 3 Gaussians. You say it means that there are 3 different types of images, because you are seeing them as mixture of 3 Gaussians, and so you are trying to model it as just one probability distribution having 3 of these peaks. So this tells you that there are 3 different types of images, and if you are trying to fit in again the 3 Gaussians in it, so you got to have so these are the 3 of them together, and if there are more pictures with forest, so it will peek out, but every image will be a point on this line. So you are going to see the same thing what you saw earlier, that if you have normalized it, it is 0 to 1. If you have not normalized it, it is 0 to 200 55. Okay, so let's say there are 10,000 images in your data set, 10,000 images. So every image will appear as a point here. Okay, so you can see the distribution of those points based on their intensity value. So all these are the points. Okay, and now if you are trying to fit in 3 Gaussians, for example, in this you start with the same. So you have one Gaussian, you have another Gaussian, you have another Gaussian, and you assign an initial probability of 1 by 3, 1 by 3, 1 by 3, first mu1, mu2. So you have to assume all these values once you are trying to fit in 3 Gaussian into this data. So this is how you start. Yes.
The number of distributions you may assume that
Yes. Bilkul. You got to assume the number of distribution. And what you can do is you may still use the knee method, where you first do it for 3, then you do it for 4, then you do it for 5. And then there is a way to evaluate that which one should fit better. But you got to assume the number of distributions also you got to assume. See? So you assume all of this, and then because you know the formula for this, formula for this, formula for this, so you can find out the probability of an image to be part of your first distribution. You can find out probability of the same to be part of second distribution. You can find out probability of the same to be part of third distribution, and use the Bayes theorem to find out what probability that given this image, how much of it is part of distribution A, how much of it is part of distribution B, and how much it is part of distribution C, which is 1 minus this and this plus this, or you can use the formula. I'll give you the same answer. So, and then use that to update the mu's and the sigmas, and again replot your mu, all these distributions, and keep doing this until it converges into, and there is no more movement of the mu's. So you say apparently this is the right assignment, and this mixture is always going to give you 1. So this plus this plus this is always going to give you 1, and area under the curve, if you plot the CDF, it is always going to be like this. So 1. It will start from 0, and I'll show you how the distribution is running from 0 to 1. The cumulative distribution is running from 0 to 1, and so we know all of this. So we know all of the mixture of Gaussians. If you say no, I want to get into 3D, okay, so means now your distribution in 3 dimensions. So your distribution will be R, G, B, and they may also be related to each other. Okay, so you are going to see in every distribution a covariance matrix, not sigma of blue, rather a covariance matrix, which is here sigma square red, sigma square green, sigma square blue, and here sigma of red and green, sigma of this, sigma of this, sigma of this, sigma of this. So you are going to see 9 values. So a complete covariance matrix. You got to assume this, 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 you got to. So once you get into the first iteration, you got to assume all the 9 sigmas, and that's how you start. Okay, for every distribution you got to have this matrix, and this is the matrix which you start updating. And there is a formula, so updation is very simple. There is a formula for sigma square R, and there is a formula for finding the cross correlation of red and green. Okay, so those are the simple formulas that you have to use to find these things out. And so you have these distributions. Now these 3-dimensional distributions will be moving, and will be getting have some pi 1, pi 2, pi 3, which is the probability of somebody to be part of one and other and other. So it gets complex. Now just imagine if in 4 dimension and 5 dimension and 6 dimension and 8 dimensions and 10 and 100 and 1000 and 10,000 and million of these distributions. So how much time it is a very high performance computer to model them. Okay, so 2-dimension is, for example, you say let's try to solve a 2-dimension problem, and we know the 2-dimensional problem is where you don't know. So these are the points, and you don't know how many distributions are there, number one. So you got to assume that these are the number of distributions. This is the very first thing you do. Then for every distribution, you got to assume where are you going to place them. Are you going to place one, for example, here? Sorry. So one is maybe here, another is here. Because you can't see data, also remember, we are just plotting it, but if it is more than 3 dimensions, you can't even see it. So you got to just randomly say these many distributions, and this is the mu, this is the mu, this is the mu, this is the centroid, and you got to have a covariance matrix for this, covariance matrix, covariance matrix, covariance matrix, covariance matrix, and the probability, if there are 4, you say 1 by 4, just to start with 1 by 4, 1 by 4, 1 by 4, and that's how you start maybe, okay. And so let's say if there are 3, so you are going to repeat the same step. For every point, you got to find out how much of this is in this distribution, how much of this is in this distribution, how much of this is in this distribution. That's what we do in every clustering algorithm, okay. So this point, first with the a priori knowledge, for the knowledge that I know this is part of a distribution. So you calculate this, there is a formula which is a very simple formula which is 1 over 2 pi under the root the determinant of your covariance matrix, okay, and then exponential minus j, and then there is an expression, okay, which is in the vector form. So you put all the values here and find out what is the probability of this point to be part of this distribution. Then use for the same point, find out the probability of it to be in B distribution. That's also very simple. Use the same formula, but now with mu's and covariance of B, and then for the C. And once you have this, go back to the Bayes theorem. Same. Now you know this, Now you say, what is the probability given I have this point, what portion of it is in A distribution, what portion of it is in B distribution, what portion of it is in C distribution. So same, no matter what is the dimensionality of the data, you are going to repeat the same thing. So what we have learned in 1D case, only this has become more complex. And the good thing about this is perhaps here is 2 over m or 2 over m, yeah, perhaps. But this is valid for not only for 2 dimension, it is valid for 3 dimension and 4 dimension and 5 dimension and 10 dimension and 100 dimension, 200 dimension. For example, in word2vec, you have a 300 dimension vector, for every word. For the natural language processing, every word is converted into a 300 dimension vector. So you can just imagine a 300 dimension vector. Okay. So this is what you first calculate using the formula, find out xi given that it is part of distribution B. Find out the probability, putting it in the formula. And so this is the 2-dimensional case where you have the covariance matrix and you have probability of xi in the B, xi in the A, xi in the C. Formula, nothing else, okay. And formula is simple, only xi is vector, ub is vector, okay, because there are now 2 components of xi. One is x direction and the other one is the y component. And once you have this, x is this, your mean is this, and your covariance is this. And then find out the conditional probability. The part given this point, how much is it in B? Okay, Bayes theorem. Find out BI, find out AI, find out CI. Okay, so find out BI, CI. This is a prior probability, which is you split it into 1, 3, 1, 3, 1, 3 if you want to. 1, 3, 1, 3, 1, 3. AI, CI for I using Bayes theorem. So you can do all of this. Then even for no matter what dimension you have, you can use this, and this has to be 1. So update your a priori probabilities, and this will start moving. As you see this animation, it will start moving, and it will take you to the true distribution. So this is the 2D. This is where you could see that how the Gaussians in this dimension and how the Gaussian and mixture in this dimension. Okay, so once you mix them together, they get you this. And this I have already shown you that every point is part of the 3 distributions. And this is the type of things you are going to see. The model is going to give you, because it's a model where you have modeled it as a 3 distribution, but it's a mixture, it should appear as just one. And once you plot it in 3D, it may appear like the, देखिए it's open book, open notes, open everything. So I want a basic understanding primarily. So we'll see that people have basic understanding and at least they have gone through the lectures. So I don't expect people just to really know the math, in gory details. I just know, okay, a sense hai na, they have understood the essence of how this is being done. So I will make some model questions and I'll send it on the group as well so that you can practice. So अब देखें, if you have data like this, it's not that you cannot fit Gaussians, but it will be an overkill to put a Gaussian to do clustering of something which looks like this, which is separated. So this data, you can see it's a cluster, it's a cluster, it's a cluster, and K-means can do a very decent job here. K-means can do a very decent job. So why to just bother yourself in getting into all the trouble of the covariances and matrices and models and yeah. So you got to decide, but if something data is like this, so there is no way that K-means is going to work. There will be a lot of errors. If it is labeled data, you are going to see a lot of errors in this, lot of errors. Okay. So here Gaussian mixture model may be the best way. If you have labeled data, you can find out which one is the best. If you don't have labeled data, so you have actually no way of knowing like this which one is the best. But
we have independent data.
You have
Which one is better, gaming or gaming?
If you have independent data, you don't know which one is better. That's what I'm saying. There are some cluster evaluation techniques that will tell you that perhaps this technique has given you a better cluster. Okay, but if you don't have a labeled data, remember, because your data is not labeled, you really don't know whether this really is a separate cluster, this really is a separate cluster, this really is a separate. So if you don't know this, okay, and that's the job of the clustering algorithm, to find out, yes, there is 4 or 5 different groups of people in this data, or 4 or 5 different types of objects in the sample space. And that's the job of the clustering algorithm. If you already know the label, so then there is no point in actually clustering them like this. But for example, for this data, K-mean is best. This is an overkill. Gaussian mixture model is an overkill. If this is the data, it will fail. K-means will fail. Okay, this will be the best clustering algorithm. Gaussian mixture model is going to be the best clustering algorithm. And please remember, this is also generative. Okay. So, and it has many applications. Yes, you can apply on. Yeah, but you know what? It is now here you yourself are just trying to fit in Gaussians. There you let a humongous amount of data and your neural networks, the weights, to by themselves get this model out for you. Okay, so that's the difference. Once you go for deep learning, you don't want to get yourself troubled into doing all of this. You believe that because you have humongous amount of data, your network can extract this model for you. So that's why people move to deep learning, but that requires a lot of data. But if you don't have a lot of data, then you have to rely on these techniques, because the model will not converge, okay, and that'll be giving you just an overfit and it'll give you the wrong results. So it has many applications.
Sir?
Yes.
Sir?
जी बताएं.
सर ये K-mean और GMM में डिफरेंस भी समझ आया वो फर्स्ट वाले एग्जांपल में इसमें ओवरकिल GMM ओवरकिल है.
जी देखिए, इस
इसमें एक जैसा इफेक्ट ही लग रहा है.
इफेक्ट तो है, ये बनाए एक जैसे क्लस्टर हैं, सो बोथ हैव रिजल्टेड इनटू सेम क्लस्टर्स. But GMM
Yeah.
is computationally very intensive because in GMM here you are only computing distances. ठीक है. K mean में क्या करते हैं, you have cluster centroid and you just compute distance of every point to with every other point with the
Yeah.
centroid, and then you keep updating the centroid, so it will hardly take any time. But here you got to have like 5 distributions, initialize with 5 distributions or 4 distributions, finding their covariance matrices, their a priori probabilities, their mu's, and then keep moving them, keep assigning every point to all the clusters. So this is computationally very intensive once both are going to give you the same results.
Okay, okay. In
ठीक है?
respect to computation,
Yes,
not GMM is
precisely. It's because of the computation. That's why I'm saying it is giving you the same result, but it's an overkill because you are using a very sophisticated technique. Okay, a very sophisticated technique to do clustering of data that can easily be clustered using k-means clustering.
Okay,
Okay.
okay, I understand.
So if the clusters are separated, then best is to use k-means. But if they are into something like this, where they are like their distributions and they are into one another, there it is best to use GMM, which is. And how do you figure this out? Usually you may have some of the data as labeled data, where you just see that which one in this part of population. For example, I gave you an example of where you want to classify Americans based on their colors. And you may have some annotated data, a sample space where you say, I have, these 500 people's data, these are African, and this is IID, like there you have randomly taken and with a large population, and you say, okay, let me just try to see which model is best to classify, and then you just take all the images and then you just classify them or cluster them into different clusters. So that's how one way of seeing it. So in image processing, for example, here you see this image, and now GMM is used to basically cluster. So here it is 5, and here there are 10 Gaussian mixtures, and based on 10 GMM, you have this image, and this is the original image. So, and, वही बात है, 10 mixtures, 10 Gaussian, mixture of 10 Gaussians. But how do you really do this? This is important. Okay, how you do this? What you do in image processing, that every pixel is going to be part of one of the 10. Let's say if it is hard clustering, so every pixel is part of 10, and every 10 is basically a color, a mu1, mu2 and mu10. It has R, G and B, it has R, G and B, and R, G and B. 3 dimension because a colored image, so every cluster head or every average value is red, green and blue. So once you cluster, every pixel will be part of the 10. Either it is part of one mixture, the other. It is soft is once every pixel is part of a little part of all 10. Okay? So every pixel will be little part of all 10. So you have to mix the colors, these 10 colors, according to their ratio for every pixel. Sorry? Every pixel has, once you have assigned them to a cluster, then forget about these colors. Okay, forget about these colors. Take a pixel, find out how much of it is part of first Gaussian, the second Gaussian, the 10th Gaussian, and take their colors, mix them in that proportion and replace the pixel. So precisely, वो तो एक पिक्सल में कर दिया था, यहाँ पे every pixel is replaced by another pixel. Okay, so this is where I'll explain it in more detail. So here is, for example, this is the original image, and this is the image if you have only 5. If you have only 5 options for each pixel to be part of. Okay, it has changed the image. But this image, if you have every pixel, you have an option to be part of one of the 10 and all of the 10 actually, a little. So this image will remain almost as this image. Okay? So this is what, once you are mixing converting in image processing, you can use Gaussians to smooth out these images to make them sharper. And how you do this is primarily first creating a histogram. Histogram is very fundamental to machine learning and modeling, especially once you are dealing with images. And so histogram is very simple that if
सर
जी
सर हम उसमें अचीव क्या करना चाह रहे थे, कंप्रेशन अचीव करना चाह रहे थे, इमेज कंप्रेशन।
जी आप यूजुअली
जैसे हमने उसको 10 डिस्ट्रीब्यूशन में या 5 डिस्ट्रीब्यूशन में
जी
कन्वर्ट किया।
precisely GMM is used for compression and also GMM is used for tracking. How for tracking? Because if you have an object which is moving, it means the distribution is moving. Okay, so some GMM, some people have used GMM for tracking as well. Okay, so in our case we are using GMM for clustering.
Okay.
Okay, but so people have used GMM in many different applications. If you look at how GMM is used, it is used for generating data as well. Okay, generating images as well. So there is a paper which takes like 10,000 images of alphabets, and then based on the GMM model, it generates 100 more images which are of the alphabets but not part of the original data set. So you can also generate depending upon which application.
So it's also used for classification.
For classification as well, you can this can be a feature. The GMM
Yeah, for recognition.
For recognition, so it could have it could have so many usages because you are getting better understanding of something which otherwise you don't really understand, an image. Okay, so you are getting a better understanding of the image, and you are getting some intelligence out of every image that you have, kind of. Okay, na? So this is like
Can be used for tracking. Can it be used for tracking the flow of a current on any surface?
yeah, if you have if you have a digital representation of anything which is flowing, which is changing its distribution. Okay, so you can actually use it for those applications as well. So histogram is very fundamental, and it's very easy to know how to plot a histogram. How you plot a histogram of a black and white image? Every pixel value can go from 0 to 255. So these are the total gray. This is pitch black, and this is completely white. So every pixel will be one of these. So what you do is you take a pixel. If let's say it is totally black, so you add one in this bin, and you find this 10, so you add one in bin number 10. Then you find the next pixel is also 10, you add 1 plus 1, 2. So it is the histogram, what you see here is a count of the different gray scales in an image, that how many black pixels are there and how many white pixels are there, and this is the peak, and this is the gray scale which is maximum, which has maximum pixels in this image. So you can find out the histogram. So this is the way that you have, depending upon that, it can have value from 0 to 15, and how many pixels are of 0 intensity, of intensity 2, of intensity 2, 3, 4, and you plot a histogram. And so once you have this histogram, then you use it for different purposes. Sometimes we do histogram equalization, and sometimes you can also model it using the GMM. So like this, if you want instead of just every image to be just part of. So I'm making a problem more complex. One is you say, okay, every face is just, you reduce every face to 1 pixel. Okay, this is what we did, 1 pixel. So everything we said, we take a patch from here, we take a patch from here, we take a patch from here, and we convert it into 1 pixel. 1 pixel, which is just the average value of the face. But what if I say, put a histogram? Okay, so the people who are white, and if I all the pixels on his face, which is the skin, taking out his hair and his eyes and eyebrows, and plot it as a histogram, so it will be more towards on the white side. His face will be more towards on the white side. And if I take a black person and plot histogram of his face, it will be more on this side of the spectrum, but now it is not 1 pixel. These are 256 values out of these, but mostly black people histograms will be more on this side, and white people histogram will more be on this side. And once I plot this, now there are not only 10 values, there are now 2 clearly defined distributions apparently, where you have you can find out that how many different types of skin people are there in the population. And you are not interested in identifying that he is black or he is white. You are interested in seeing the distribution of different color people in the population. And do you see a distribution? Are you fitting 2 Gaussian? You are fitting 3 Gaussian? You are fitting 4 Gaussians? And that will help you to figure out that how many of these are there, and what is the population, what is the percentage of a population which is in this distribution and in this distribution. So you are doing a generic clustering and classification. So you can do this. Let me, this is what we did in K-means, but let me come to something which I wanted to discuss, and we will come back next time. And also we are very lucky that we have Dr. Zaidi sitting with us. Sir is Pro-Rector Academics in GIKI, and also is the founder of SEEKS. As we know, perhaps, not really perhaps, SEEK is the best engineering institution of the country, and we are lucky that Sir is here. So, and also Sir, November has just passed, so I thought about, somebody also asked me कि जी इकबाल की शायरी के साथ कुछ करें. अब इसको I have tried to mix. So there is a proposal to work on a